what I want to do here is kind of help you establish a basic strategy for finding limits and then work out a couple more examples. First thing you want to do is you want to learn to recognize which limits can be evaluated by direct substitution. This is making reference to polynomials and rational functions. Radicals. We can evaluate a limit of a radical with direct substitution under the right conditions, that being dependent on what the index is. Polynomials are great. We need a limit of a polynomial. A direct substitution always works. There's nothing to worry about there. It simply always works. And that's because polynomial functions are defined everywhere. There's never an issue. Number 2 here, if the limit of f of x as x approaches c cannot be evaluated by direct substitution, then want to try to find a function g that agrees with f of x at x other than x equals c. That's some of the stuff that we just got done doing. The idea of finding an equivalent function. Typically, we'll see if we can factor, and if we can factor out the numerator and denominator and actually cancel out the factor that creates 0 in the denominator, then usually we can easily find a limit. We end up with something that we can use direct substitution on. Now, we want to apply the previous theorems to conclude analytically then that, as we said previously, the limit as x approaches c of f of x then is equal to the limit as x approaches c of g of x. And I've done a couple of examples using that particular idea. So let's take a look at a couple more possibilities here. A couple techniques that may come in handy. One is called the dividing out technique. I guess that's the proper term. Who knows what's really called, but that's what we're going to do. We're going to divide stuff out. X cubed minus 5x squared plus 7x minus 3 over x minus 3. And I want to take a look at the limit as x approaches 3. Well, if I think of all this as f of x, it's a rational function, so let's just find f of 3. Now, when you evaluate that, what you're going to end up with is 0 over 0. There's a problem. So, x minus 3, because when x equals 3, I get 0 in the numerator, then x minus 3 must actually be a factor of the numerator. So if I can factor this out, I should be able to cancel out this denominator, x minus 3, and be in good shape. I suppose there's a couple different techniques you could try to use to factor this thing out. Nothing looks really good to me off the top of my head. So what I'm going to do is long division, hence the dividing out technique. I'm going to take x minus 3 and simply divide it into x cubed minus 5x squared plus 7x minus 3. Do long division of polynomials. Well, how many times does x go into x cubed? Well, it goes in x squared times. So I'll have x squared, multiply it, I'll get x cubed minus 3x squared. So I need to subtract that component. And when I do, this becomes negative x cubed, so that's a 0. This becomes positive, so this gives me a negative 2x squared plus 7x minus 3. Now, how many times does x go into 2x squared? Well, that's minus 2x times. When I multiply this back out, I'll get a negative 2x squared plus 6x. Again, I need to subtract this. This becomes positive, cancels out. This becomes negative. This is then x minus 3. How many times does x minus 3 go into x minus 3? Oh, one time. And I'll multiply that. I'll get x minus 3. I'll subtract it, and I get 0. As I should, because I said that x minus 3 must be a factor of the numerator, because I end up with 0 over 0. So, what I just found was my g of x. So I am now going to take a look at the limit as x approaches 3 of this g of x, this equivalent function. X squared minus 2x plus 1. These agree everywhere except when x equals 3. So if I take the limit now where x goes to 3, I end up with 3 squared minus 2 times 3 plus 1. So I'll get 9 minus 6 plus 1, or this limit is equal to 4. Now, you may want to grab Maple or something and produce a graph of this. And put them on the same set of axes together. And take a look and convince yourself that these are, in fact, equivalent functions. They're equal everywhere except when x equals 3. When x equals 3, this function is going to have a hole in it. That's what this ends up telling us in this particular case, where this function is continuous. And that's what allows us to use it to find the limit. Another technique that's kind of along these similar lines of what we've been doing is a rationalizing technique. So I need to find the limit as x approaches 0 of x, square root of x plus 2 minus the square root of 2. Well, if I simply evaluate this, if I call this f of x, I simply say, well, gosh, that must be equal to f of 0. F of 0 is the square root of 2 minus the square root of 2. Well, that's 0, so no big deal. 0 in the numerator is never a real big deal. Over 0. So this is 0 over 0. Well, that is a big deal. Okay, so what am I going to do? I can't factor this. I mean, long division is not going to work. But what I can do is use a rationalization technique. If this was in the denominator, back in algebra and probably pre-calculus, you would have rationalized the denominator. Well, let's use the same technique to rationalize the numerator and see what happens. So I'm just going to work on a little bit of algebra here. And I'm going to take the square root of x plus 2 minus the square root of 2 divided by x. And I'm going to multiply this by the square root of x plus 2 plus the square root of 2 divided by the square root of x plus 2 plus the square root of 2. I multiply by 1. Now, this is a conjugate in case you didn't recognize it. So when I multiply this out, because it's plus and minus, it's like the difference of squares. I'll get this squared minus this squared. So this p squared is simply going to be x plus 2 minus square root of 2 squared, which is minus 2. And then divided by x times the square root of x plus 2 plus the square root of 2. Well, obviously, that's going to cancel like that. So this is going to be equal to, again, I'm still doing algebra here. I haven't done any calculus yet. X over x times the square root of x plus 2 plus the square root of 2. Well, these x's are cancel. So this is equal to 1 over the square root of x plus 2 plus the square root of 2. So this is actually equivalent to that. Because I multiplied by 1, that's a fair thing to say. So what I need now is simply take the limit as x approaches 0 of 1 over the square root of x plus 2 plus the square root of 2. Now see, as x goes to 0, I simply have the square root of 2 here. So this is going to be equal to 1 over the square root of 2 plus the square root of 2. So this limit is going to be 1 over 2 root 2. And to take it one more step algebraically, we want to rationalize the denominator, so multiply by root 2 over root 2. And when I do that, I ended up with root 2 over square root of 2 times the square root of 2 is 2. 2 times 2 is 4. This is root 2 over 4.